So part 1 of BS7671 says protective equipment should be able to withstand the fault current at wherever the protective equipment is installed. So there's the main fundamentals of what we're trying to achieve. Under definitions, prospective fault current is, as it says there, is the overcurrent. Remember, that's in excess of the cable rating. Any given point in a circuit resulting in a fault of negligible impedance, so that's dead short, effectively, between live conductors and also between live conductors and an exposed conductive part. So it's basically saying which is the biggest fault current. Everything's got to be able to withstand that. Until you get to chapter 43 of part 4 of BS7671, that it's basically saying that all protective devices, wherever they happen to be installed, it says they should be able to protect against overload and fault current, shall be capable of breaking, in other words disconnecting, and for a circuit breaker making, obviously a circuit breaker can be reset unlike a fuse, any overcurrent up to and including the maximum prospective fault current at a point of which they are installed. So that's what we're trying to achieve. So that's the main fundamental principle. Then when you get to part 6, which is obviously inspection and testing, it says that we should work out or figure out what the earth fault loop impedance is for the installation. And as it says on there, it should be measured or determined by an alternative method. It says an electrical continuity test shall be carried out in accordance with 643.2 before carrying out earth fault loop impedance measurements. So continuity should be carried out, as you're probably all aware, before an earth fault loop impedance and not the other way round. Prospective fault current then, the prospective short circuit current and prospective earth fault current, so that's the PSC and PFC, shall be measured, calculated or determined by another method at the origin and other relevant points in the installation, and therefore that ties up with the other regulations that we just looked at relating to protected devices, and that is that they should be able to withstand whichever is the higher of the fault current at the locations of which they are installed. Looking at the electrical installation certificate, which is obviously where you're going to record this, and its nature of supply parameters relating to the earthing system that you have come across, obviously nominal voltage, so U and U0, which means line to line for U or line to earth for U0, and then the frequency. It says on there, number 1, by inquiry. To be quite honest, if you've got to inquire what your voltage is and the frequency is, I don't think you should be touching electricity, do you? But this is the bit we've just been referring to, and that is prospective fault current. And it says number 2 and number 2, and against earth fault loop and fault current. It says by inquiry or by measurement. Remember, if you do by inquiry, electricity companies will quote you the maximum fault current and the maximum earth fault loop for that particular supply if they happen to know it. Therefore, we're more likely, to be honest, to measure them. And this is the measurement that we've been referring to, and it says IPF, which is prospective fault current. Remember, it's not interested in which one it is, it's just after the biggest fault current at that location, because these devices and any devices at this point must be able to withstand that breaking capacity, and therefore ZE is also recorded. But this is the origin, remember, where you record it, but it's not the only place you record fault current because it goes on the schedule of test results as well. And this is the schedule of test results, and therefore this is where you put the fault current for the distribution board. So obviously if this is your distribution board at the origin, then this fault current here will be the same as the one on the characteristics of supply because it's at the origin as well. But they just refer it to it slightly different. They say IPF at the dB because in installations you have more than 1 dB, the chances are. And also they refer to it as the ZS at the dB. But if this distribution board is at the origin, then this ZS, the ZdB, will be the same as the ZE on the characteristics of supply. So as we'd said earlier on, that you need to find the fault current at each location to which you're installing it. Because you're looking at the protected devices that you install to ensure the breaking capacity here is equal to or more than the fault current that is available at this location. So for ZE, we want to make sure the isolation is off, the installation is off, because what you're about to do is remove the main earthing conductor. And obviously the last thing you want to do is take this earthing conductor out with the supply on, because if you do, chances are you could electrocute yourself or someone else in the building, because there could be fault current passing through this conductor if the installation is still on. So it's essential that this is locked in the off position. So set to loop on LPE, and now we're interested in the ohmic value and not the fault current that it will display. And then with your earth fault loop impedance meter, we want to put that on the earth. And remember, these here are live. So with your meter, and press the test button, and 0.39. Prospective fault current on TT installation. So basically the fault current that we're looking for on the test sheet, as we've already looked at, is the maximum amount of fault current that will flow between any particular fault. And in this case, we're looking at the origin of the installation on here. So what do you need to do it? Well, it can be done by inquiry, and the electricity companies will quote you maximums, which in the on-site guide is given to you as 16,500 amps if you're in London, 16,000 amps, these are single phase, or three phase would be roughly 33,000 amps is what they would quote you for a supply up to 100 amp supply. Remember, anything bigger than that, supply-wise, the fault currents could go up because everything gets a little bit bigger. So just looking at single phase, what we tend to do is we tend to measure it and record it. So first things first, obviously ensure the installation is turned off, because this is, although it's a live test, the isolator is in the off position. So we can check the external fault current is what we're looking for. And basically what I say to all students when working out fault current or measuring it is, I would say to people, think of the fault current, if not that you should try it, but if I gave you a spanner and said stick it between two conductors that would make the biggest bang, where would you put it? So we'll start off with a TT installation, because that's effectively what we're trying to find. We're trying to find which conductors would make the biggest bang if you was to ever short them out. Not that you should try it, for obvious reasons. So we'll look at a TT installation and working out the fault current, or calculating the fault current, or measuring the fault current. And measuring is what we're going to look at. So here's an installation, and what we must make sure is the isolator is turned in the off position. All the bonding and connections to earth must be maintained, so they should stay on the MET, because unlike ZE is where you want to remove the parallel paths of earth. Now in fault current we want the parallel paths, because when we have a fault, current will take any path possible back to the start point of the transformer, wherever that happens to be. So if that happens to be back through bonding pipe work, and that's a better return path, that's where it will go. So everything must be connected, but remember, this is locked in the off position. So we only want to test the outgoing circuits at the origin. So the meter you would use would either be a 3-lead or a 2-lead instrument. 3-lead, if it was a 3-lead, basically what you're looking for, one goes on the line conductor, and we're connecting on this side of the isolator. One would go on the neutral and one would go on the earth. Now what you would have to do is you would have to basically set your meter up to read which fault current you wish to record or find out. Now there are two main ones they used to be referred to, and if you're familiar with a fluke instrument, you can set it to either the PSC or the PFC is what comes up on your display. And basically you have a button, and this is the same on the Megas as well. It goes L and N is the selection that you're looking for fault current, and on the fluke ones, and I'm not sure what the Megas do, can't remember, but it comes up as LPE. So L to N is the prospective short circuit current between live conductors, is ultimately what that is, and LPE is prospective fault current from live conductor to earth. Obviously the line conductor is what we're referring to here. So these are the two that you're looking to record for a single phase installation, and that's what we'll concentrate on. So the meter will be a 3-lead meter, like I say, the line conductor on that one, the neutral conductor on this one, and the earth connects straight to the MET, and you're going to record everything. And then when you record it, you'll press the button, and what it does, it sends obviously it measures the voltage, it sends a known current out, and internally it does an Ohm's law calculation to work out what the fault current would be. So where does that current actually flow? Well, when we do a PFC, we do this one here, the fault current is going to flow up here, down here, and through your meter, and then it will take whichever path back to this point here. So let's just keep it simple, and it will do that route there. So this one is the PFC. Now that will depend on your ZE. So if we were to do a quick calculation, what that would be, so that can be calculated because you'd know that's based on the ZE calculation. However, just bear in mind your ZE calculation is based on this remove. So it would be this ohmic value here. So if we were to look at this, and typically in a TT installation, this value here is going to be quite high in value. So let's assume it's up to its maximum of 200. So that would be calculated, the fault current will be calculated by U0 divided by the ZE of that installation. So that's 230 divided by 200, which is the maximum allowed. That would be 1.15 amps. So basically, if you shorted out that conductor down to there, that's how much current you would get to flow. Chances are it'd probably be slightly higher in real life because obviously this is a maximum and it depends what parallel paths you have. So in our example here, you'd have 1.15 would be the fault current to earth. But obviously the test sheet requires the biggest fault current would be the line and neutral where the fault current is likely to be. And that one then we'll to put down as an orange dotted line if we can see this. So this is going to do a fault current around this path. And typically we don't tend to measure the impedance of this thing here. You're quite capable of doing it, but this is where you'd set your meter up, and now when you select it to LN, the chances are what your meter will do is it will say it doesn't need this third lead. So this lead would disappear off your meter and say it isn't required, and you only have one on the line and one on the neutral, and you press the button and you'd get a reading and it would display a reading, and let's make a figure up, it would become 640 amps is the fault current in my example if your meter was to read that, obviously. So what do you write on your test sheet? Well, you write the highest out of the two in this case. So you'd actually, because it's Ka is what you're after, it would be 0.64 Ka as the maximum prospective fault current for this particular TT installation. Remember, the whole point of doing the prospective fault current is to make sure the protective devices installed in this location can withstand this breaking capacity. So now fault current for a TNS installation. So TNS, we have our same installation here, so we've still got our bonding connected, everything stays connected. Remember, main switch is turned off and locked in the off position because this wants to be the installation dead. But all bonding must be in place. So we've got the same again. We've got basically where would the biggest bang be, which conductors were to short out. So would it be line and neutral, or would it be line and earth that would make the biggest bang? And now it's not quite as straightforward as a TT where you pretty much know it's going to be the line and neutral. Now it's unknown because it does depend what the sheath is made of, what size that is, and it's an unknown quantity because you might see the cable come in and you might see the actual sheath is a lead sheath or an SWA, and you might think, well, that's not as good a conductor compared to copper, so therefore it's probably going to be line and neutral. However, what I would say to that is the cross-sectional area of that lead or steel wire armoured sheath will probably be larger than the copper conductors inside. So that may balance out in its favour to be the highest fault current at that point. What you also don't know is what happens when the cable gets out into the road or the pavement where it joins a much bigger cable. So you don't know what happens to the cables beyond your property, and therefore we need to work it out or measure it is the best way to do it. So we need to do the same test again. So we are looking for, remember, locked in the off position, we put a line conductor on there, a neutral conductor on there, earth conductor on there from your meter, from your earth fault loop impedance tester, and we set it to fault current, and we want to set it to measure the LPE first, and we will do a fault current, remember, again, and it will flow around in this location. So I'll just put it on again. So down there, and it flows now back through the sheath and around. So that then is the PFC. Now you might measure ZE, obviously you would have measured ZE. Remember, ZE, is with this earthing conductor removed from your bonding, because now you don't want parallel paths on ZE, whereas fault current you do want the parallel paths. So if you got this, the maximum ZE for this one would be 0.8. However, if you was to do the test again with the bonding on, you might find that the 0.8 actually comes lower, which is why you want it on, because you want the biggest fault current that may occur. But let's assume it was the same. So that would be 230 divided by 0.8. So you would get 287 amps would flow to earth if that was the case. So this would be the smallest amount of fault current that is likely to flow on TNS installations. Chances are it'll be a lot larger, but we need to know the largest out of these two. So you then press your meter to set to LN, okay, between live conductors, so in other words between these two, and now the fault current is going to go, remember it's probably going to be a 2-lead test on your meter now, and it's just doing these conductors here, okay, and that will come back with a value, and it might come back with 480 amps as an example. And again, which one are we going to write down? We're going to write down the highest of the two, so you'd actually be writing 0.48 Ka on the fault current for this particular single phase installation. Prospective fault current for a TNC-S installation. So we need to know that the main switch is locked in the off position, all bonding is in place. Prospective fault current is either going to be the between line and neutral, or between line and earth is where the fault current is going to be. So if you could calculate it again based on these values here. So again, 230. And remember, ZE would be a maximum of 0.35. However, remember this 0.35 would be measured with this earthing conductor removed from the MET, so you remove parallel paths. With it now connected, this value may be lower. It would depend where your bonding goes. If it goes to pipe work that goes physically to ground, which is a true extraneous conductive part, it would probably bring the ohmic value down. How much by? We don't know. That's why we have to check it. But let's assume it wasn't. It was this. So you would do this you could do this as a calculation. The meter would give you a more precise reading, but it would give you 657 amps. That would be the fault current to earth, and remember that's the red line here, so that's coming down here and it's going back up and through that way there. So that then is the prospective fault current there. What we also need to know is we need to know the PSC. Now, hopefully what you can realise now then, because this is at the origin, the chances are if you did do this calculation, do this measurement between line and neutral, you would press it over to LN. It requires 2 leads. It's now going to connect between there and doesn't require this one. So now the fault current is going to be this loop. Lots of dots on here now, but what I hope you realise at this point now is that the difference between the two is not a lot, because the only thing that's slightly different is this conductor here, and this is the earthing conductor, and this earthing conductor for a 100 amp supply is going to be a 16 mil, and probably no more than 2 meters in length. So a bit of 16 mil, 2 meters in length is not going to make a lot of difference in its ohmic value to the overall circuit. So it probably won't be a million miles off this figure here. So on a TNC-S installation, the chances are the PSC and the PFC between the conductors may well be the same, because in theory they're effectively measuring exactly the same thing. But the irony of these things, when you do measure them, every time you press the test button it alters slightly. But then that because the voltage can fluctuate and a number of reasons. But hopefully that's what you would get. So what we would now write is 0.657, my apologies, Ka for this particular installation. Mentioned three-phase. All we've gone on about for the last 20 minutes is single phase. Well, don't worry, three-phase. So in Appendix 14 of BS7671, it says you should work out the fault current, because as I said earlier, the biggest bang is likely to be between in a three-phase installation. If I gave you a spanner, the chances are you'd stick it across two line conductors. 400 volts, going to give you a much bigger bang. So what do they do? Well, you could put your meter across it. However, I would read the instructions before doing that, just in case your meter cannot do it, and it will actually destroy your meter. So please read the instructions before putting your fault-free impedance tester across a couple of phases. However, what we can do is just use a simple calculation, and it is possible to just multiply it by the square root of 3, which square root of 3 is 1.732, but obviously maths isn't particularly my strong point in that sense, so multiplying any number by 1.732, I'd need a calculator to do it. So what do they tend to do? Well, there's your 1.732 here, which is the root 3 between line conductors. However, the biggest bang actually would be if all line conductors were shorted out in the unlikely event, and all they say now is just multiply by 2, which is much easier to calculate. So what do you do? Which are the two values that you've been measuring, the PFC and the PSC? Well, the one you actually multiply is the line and neutral. So in other words, what you do is multiply the PSC by 2. Don't do the PFC. So PSC multiplied by 2, and that then would become your maximum braking capacity, your prospective fault current at that point in the supply when you have three-phase.